Hello guys, hi everyone, welcome to Easy Tech. In the previous lecture, we solved two problems on O.C.C curve. Those are the most important problems. In this lecture, I will explain what is the voltage regulation of generator. See, suppose if you want to find out a machine performance, there are two indices are required. One is efficiency and another one is regulation. If you take a person, how can we know the person's performance based on his marks? His marks represents that he is a clever guy or is poor in subjects. Similarly, same way, by knowing the efficiency and regulation, we can tell that the machine performance is poor or good. If you go for the generator, we should concentrate on voltage regulation. If you go for the motor, we should concentrate on speed regulation. The efficiency is common for generator and motor. For a transformer also same thing, efficiency. The efficiency of a transformer is 95 to 99 because it does not consist of rotating parts. So that we will see in the next chapter. So how can you define voltage regulation of a DC generator? So it is the change in no load voltage, no load terminal voltage and full load terminal voltage divided by full load terminal voltage into 100. No load, under no load operating condition, if I am taking a separately excited DC generator, the terminal voltage of DC generator is Vt. So the generated EMF is Eg. Under no load conditions, the Ia value is small and we can write it as E minus E naught minus full load SVT divided by Vt into 100. It is the change in no load voltage minus full load voltage divided by full load voltage. It is expressed as a percentage fraction of full load terminal voltage. That is called the terminal voltage or load voltage. The voltage which is appeared across the load in a DC generator, we can call it as terminal voltage. So I will take one problem. It 25 kilowatts 250 volts shunt generator delivers rated current at rated voltage on removal of load, the terminal voltage rises to 275 volts. Determine the voltage regulation. This is a problem, simple problem. Determine the voltage regulation. So what is the solution for this one? So rated current at rated voltage, yes, the terminal voltage is 250 volts. The terminal voltage is 250 volts and the terminal voltage rises to 275 by removing the removal of load, means the no load voltage is 275. Then percentage regulation formula, voltage regulation formula, E naught minus Vt divided by Vt. E naught minus Vt by Vt, 275 minus 250 by 250 into 100, then you will get 10%. So this is 25 by 250 into 100, so 10%. So this is a problem on voltage regulation. So the next concept is characteristics of DC generator. Characteristics of DC generators. The first characteristics are magnetization characteristics. Magnetization characteristics. And the second characteristics are load characteristics. So in order to draw the magnetization characteristics or open circuit characteristics, already we discussed in the last class, magnetization characteristics are drawn between E versus IF by maintaining speed of the prime mover is constant, and this characteristics is also called as a no load characteristics. This characteristics is also called as no load characteristics. So if I am taking E naught on y axis, IF is on x axis, E is equal to, or Eg is equal to 5Zn by 60 into P by A. Once design is over, this term is constant, this term is also constant, number of conductors is also constant, 60 is also constant. Then Eg is directly proportional to N phi. As I said, when you are drawing magnetization characteristics, the speed of the prime mover is maintained as constant. Then Eg is directly proportional to flux, and flux is directly proportional to field current. As field current increases, number of flux lines increases, generated EMF is also increases. As field current further increases, the number of flux lines are increases, generated EMF is also further increases. Still, if you are increasing the field current but the flux increases but with lesser amount, the generated EMF is also with lesser amount. What is the meaning of this? Means if a flux increased by 30%, field current increased by 50%, now flux only increased to 30%. So up to knee point, the curve should be linear. After this, even if you are increasing the field current, the voltage is not produced that much. So this voltage is called the no load voltage or open circuit characteristics. We are not applying any external load on the DC generator. We are observing that it is called the internal characteristics also, we can say that, but these are the open circuit characteristics. Yes, open circuit characteristics. This is called the O.C.C curve, and below this linear portion, this OA line is called the linear region, and AB is called the non-linear portion or non-linear region. Okay, and this is at speed, this is at one speed, if you are decreasing the speed and maintain the constant, suppose previously the speed will be 1500 rpm. If you draw the curve E versus IF, and this is the first curve, n is equal to 1500 rpm or n is equal to n1. If Eg is directly proportional to n5, if n decreases, our generated EMF is also decreases and maintained as constant. That is very important. I am drawing the curve for 1500 rpm. I am drawing the curve for 1400 rpm. Is this shift downwards or upwards? Downwards, definitely. So this is for n is equal to n2. And still, if you are decreasing the speed, then the curve will shift downwards. And in this case, n3 is less than n2 is less than n1. And the next characteristics are load characteristics. So load characteristics. So these are further divided into internal characteristics and external characteristics. The external characteristics, if you take a armature, the external terms are terminal voltage and load current. So the curve between Vt versus IL, the speed is maintained as constant. If you want to draw the internal characteristics, Eg versus Ia, okay. So previously that is a magnetization characteristics. Why it is called as a magnetization characteristics means the field current which will produces a magnetic field. So to magnetize the core, which current is required? Field current is required. That's why the curve which is drawn between generated EMF and field current is called magnetization characteristics. Okay. So here the first characteristics are characteristics of separately excited DC generator. So here armature generates the voltage. You can connect a voltmeter across the armature and the armature is driven with the help of prime mover, and the field winding is connected with a variable rheostat. That too, it acts as a potential divider. So this is the rheostat we are using, and here we are giving the DC supply, 220 volts DC supply, and like this we are connecting. Why means initially the 0 volts will be applied. The flux in the field winding is only residual flux. After that, if the number of turns are increasing in this fashion, if the number of turns are increasing in this fashion, then the voltage appeared is increases, then the field current is also increases, the number of flux lines are increases, the cutting action is also increases, then the generated EMF is increases. Okay, field current increases, number of flux lines increases, generated EMF is also increases. So anyway, we know that E naught is equal to phi Zn by 60 into P by A. Phi Zn by 60 into P by A. So E naught is directly proportional to N phi, is directly proportional to flux, is directly proportional to F. So if you draw the characteristics E naught versus IF, then it should follow the characteristics are like this. So just now we discussed. This characteristic is called the O.C.C characteristics. and at this point is called the saturation point. Even though field current increases, the flux produced by the field winding is almost constant. The generated EMF is also constant. Then we should draw the load saturation curve. Load saturation curve. So this is the graph of terminal voltage versus field current when the generator is loaded. But in this case, if you observe, the generator is not at all loaded. It is under no load condition. So the armature current is flows through the or delivered by the source, that is called by the armature. As load increases, load current increases, and it is coming from the armature. The armature current is also increases. And then armature reaction is also increases. The effect of armature flux on field flux is also increases. Then it will produces some drop. It will decreases from E0 to E due to the armature reaction. There are two drops are there. Drop due to armature reaction, that is called the first drop, and the second drop is drop due to armature resistance, and third drop reduction of field current due to 1 and 2. But this is not there in separately excited DC generator. Why? Because the field winding is separately excited. In separately excited DC generator. Yes, again, so due to armature reaction, E0 is decreases to E, and IA increases means the second step IARA increases, where VT is equal to E minus of IARA. If IARA increases, then the terminal voltage will be decreases. Now I should draw the characteristics of a load saturation curve. VT versus IF under normal operating condition, under no load condition, VT is equal to E0. The reference value is E0 only. This curve is called the O.C.C curve. Once it will be loaded, the curve will be shifted downwards. Why? Because due to the armature reaction, this drop is called the drop due to, this gap is called the drop due to armature reaction. And the third one, again one more drop is also there, that is called the IARA drop. So again the curve will be shifted downwards. If you draw a curve, so this is a curve like this. Okay, this is a O.C.C curve. So this is a field current at this point, and at Q point on the PQ, and this one is R. This is called the C. It will reduces from P to R. As P to R, the curve will be reduces, means generated EMF is decreases. And the next characteristics are internal and external characteristics. Internal and external characteristics. So if I am drawing the curve between VT versus IA is equal to IL, I am representing the two curves in one line. VT is equal to EG minus IA into RA. Under no load operating condition, VT is approximately equal to EG, that should be equal to E naught. As I am taking the reference, as load increases, IA increases, that means load current increases, IA increases, armature reaction increases, then the terminal voltage will be decreases due to the decreasing in generated EMF. Due to the decreasing in generated EMF, the terminal voltage is also decreases further. So if you draw the curve between these two, so the terminal voltage will be decreases like this. This drop is called the armature reaction drop. This drop is called the armature reaction drop. Still, if IA increases, RA drop is also increases, then the terminal voltage will be decreases. So let us say one example, VT is equal to E is equal to 200 and IA under no load condition is 1 ampere and armature resistance is 1 ohm. And if IA increases to 20 amperes when the load current increases, let's check it. The VT1 is equal to E0 minus IARA. E0 is equal to 200 minus 1 into 1, that should be equal to 199 volts. As the second case, there is no change in the no load voltage, as 200 minus IA is 20 into 1, the voltage is 180 volts only. The drop is also, you can observe, it is very small, and I am representing like this with a black line. So now this drop is due to IARA drop. From no load to full load, the terminal voltage the terminal voltage is almost constant. That's why this is used for electroplating and electro refining applications. And the second one is battery charging also. These are the applications of separately excited generator. So based on the characteristics, we can tell the applications. So I think you understood. There are two major drops. One is called the armature reaction drop and another one is armature resistance drop. So if you are considering these two drops, the terminal voltage will be decreases from E0 to some voltage. From no load to full load, the terminal voltage is almost constant. That's why it is used in battery charging and electroplating and electro refining applications. So thank you guys. We will see what are the characteristics of DC shunt generator in the next video. DC shunt and DC series and compound. Thank you guys.